We are pleased to have Jonathan Pritchard here today. Jonathan's works at Imperial College. He's a senior lecturer in astrostatistics, I believe, and he works on cosmological problems, in particular looking at the early universe. We'll hear more about that from him. So yeah, Jonathan was before Imperial. You were at Harvard, Smithsonian Center for Astrophysics. And I think before that maybe you were at Caltech in the USA, and before that at Cambridge, I think, for your PhD, weren't you? So we're going to find out more about what I think is one of the most exciting areas in cosmology at the moment, which is the period sort of after the Big Bang, or before really we started to get the structure in the universe that we can see today. And it's an area of the cosmology that we really don't understand very well at the moment, and Jonathan's going to tell us all about how we'll find out more.
Thank you for having me, and thank you for that introduction. Yeah, I'm Jonathan Pritchard, as you heard, at Imperial. And this is very much a talk that's in two parts. So I wanted to say a little bit about the cosmic dawn, which is really the time when stars formed for the very first time and their light started to illuminate the universe. And then talk about some of the ways in which a new generation of radio telescopes are starting to give us some insights into this period, which we haven't seen before in radio telescopes. And so, in the spirit of radio astronomy, this should be a radio quiet zone, so please switch off your phones. That's a joke. This is a sign from the Jodrell Bank, one of the largest radio telescopes. So you heard about me. I mean, just the academic career takes you all over the place. I grew up in Somerset and went to university in the UK. Then I got fed up of always being cold in this damp climate and went out to sunny Southern California, where for 5 years it was gloriously warm. Moved to Boston for feet of snow and came back to the UK about 5 years or so ago, where I'm based at Imperial and do research on sort of cosmology, but also the sort of big picture of astrophysics. There's a lot of arguments about whether cosmology is all to do with just fundamental physics and whether things like galaxy evolution should be included in that. And a lot of the work which I do is funded by the European Research Council. I don't normally mention my funders, but especially at the moment it feels like I ought to. And if you care about the collaboration that's funded by our involvement in European agencies like the ERC, please write your MP and say that that's important. There's a lot going on there at the moment. So I grew up in Somerset, where if you go for a walk in the landscape, you come across a lot of sites of historical and archaeological interest. So Stonehenge is just down the way, there are lots of hill forts. And with archaeology, you try to find the oldest things that you can and study them close up in lots of detail. So when it comes to astronomy, we can't get close to old things, but we can still see them. So because light travels at a finite speed, when we look further away in the universe, we're seeing the past, quite literally. If you look at something like the moon, you're seeing that when it was 1 second ago. The sun, you're seeing it at its age when it was about 8 minutes ago. And so when we look out of the universe, we don't get a choice of which moment in time we see, but if we look at different distances, each distance corresponds to a different moment in time. And so we have an advantage over archaeologists that we can see cosmic history playing out in front of our eyes. Now, those distant objects only age at the same rate as we do. We can see them in their past. So if we look out of the sky, what do we see? So amateur astronomers, I don't need to tell you very much about that. You probably know the night sky far better than I do. But what you see really depends upon the frequencies that you're looking at. So the gas between stars, between galaxies, absorbs different frequencies of light. So at some frequencies you can only see stuff from within the galaxy. Other frequencies you can see much further away. And the different technologies that we have to see different wavelengths affects the sensitivity with which we can see. So different wavelengths, different technologies give you insights into things at different distances, but in a complicated way. And if we want to look at the sky from the ground, it's really the visible, for obvious reasons, and then radio waves, which pass through the atmosphere and can allow us to see quite a lot of the universe. So the sort of science which I'm interested in is bookended really by two main observations. The first of which is observations of the cosmic microwave background, which have really been led by this satellite, the Planck satellite, which you may have heard about over the last few years. So this is a European Space Agency satellite looking for the afterglow of the very hot early universe. So as that hot early universe cooled, at the time about 400,000 years after the Big Bang, it transitioned from being opaque to light to being transparent. And we can see light streaming to us from that point 400,000 years after the Big Bang to the present day. If you look at it, it looks mostly the same in all directions on the sky. But if you turn up the contrast, you start to see different temperature fluctuations. So there are hot spots and there are cold spots at the level of about 1 part in 10 to the 5. And this map which you're seeing is essentially a baby photo of the early universe. You know, if you imagine that the universe today was in its 80s, the universe is about 13.7 billion years old. 400,000 years old would correspond to about 1 year. So it really is sort of a baby or a toddler sort of age. And so by studying this, we can hope to learn about what early conditions in the universe look like. These small temperature fluctuations correspond to slight differences in the amount of stuff, how much gas there was. And over cosmic history, under the action of gravity, these slight fluctuations provide the seeds that grow into the galaxies and filaments and other large structures that we see in the universe today. So at the other end of the scale are galaxies that you can see in the more local universe. So this is the Hubble Space Telescope. When I was in the US, I was a Hubble Fellow, so this is one of my favorite telescopes. I don't know how many of you saw the movie Gravity. Did you cry when you saw the Hubble Space Telescope destroyed at the beginning? Sorry for spoilers. I sort of welled up a little bit. It's been an amazing telescope and a real workhorse, producing amazing photographs of the universe like this. But the Hubble Ultra Deep Field, which is probably the most famous of the Hubble's images. And so when you look at an image like this, which is only of order the size of the moon on the sky, each of there are a few stars in here with these little cross spikes, but most of these objects are galaxies at different distances away from us, some bright, some faint, and a range of different colors. So you can try to study this and get a feeling for what galaxies are like near to us. Some of these are very distant galaxies. The most distant galaxies that you can find in the Hubble Deep Field formed when we're seeing them rather when the universe was about 1 billion years old. Now, even 1 billion years is quite mature in cosmic history. The sort of stars that were forming in most of the galaxies here are quite similar to the ones that form in the Milky Way and the local universe and in the Sun. So this is already an evolved picture of the universe. And so just by way of explaining how we try and work out the distances for these objects, you can use colours to try and understand how far away these galaxies are. So if you look at a typical spectrum of a star, so you've got of a galaxy, you've got the wavelength, you've got some measure of the brightness, and typically there's a fairly sharp break in the spectrum that comes about because of absorption of light from the stars by hydrogen gas. And if you place this galaxy at different distances from us, the light from this will be redshifted, stretched, and this break will move about in wavelength. If you observe that galaxy in different color filters, which are sort of shown above here, in some of those color filters you'll see the galaxy, in others you won't. And the position of this break, from that you can work out what's called the redshift of the galaxy, which tells you about how far away it is. So you can try to use this to count the number of galaxies at different distances, learn about their properties. So this is sort of the state of the art, and if you put that together, then what we have is the cosmic microwave background, which is telling us about the very early stage of the universe, with these fluctuations which over cosmic history, grow into the galaxies that we see in the Hubble ultra-deep field, which reaches back to about 1 billion years after the Big Bang. But between those two observations is a period of the universe that we've yet to observe and collect data on it. It's a sort of a missing period of the cosmic history. If you permit me a Los Angeles movie reference, this is like a missing reel in the great movie of the history of the universe, The Missing Reel. And it's really this period of cosmic history which is the focus of my research. So let me remove that. And within this period, there are sort of 3 phases that astronomers have come to describe. There's a cosmic dark ages, so immediately after the cosmic microwave background forms, you don't have stars yet. You just have the sort of cooling ember of the early universe, which is dark. Now it's not uninteresting. There's gravitational collapse of material onto overdense regions, which will form the filaments and voids and other structures later. Eventually, you start to get the first stars switching on as gas collapses and can produce nucleosynthesis. And so you have starlight. So you have a dawn. So you have a cosmic dawn in a slightly poetic way. But it really is the first time that starlight is illuminating the universe. And then you have a phase transition where that light slowly creates a phase transition from a cold, neutral universe to a hot, ionized universe. And these are sort of 3 interesting phases that I'll say a little bit more about. So the first bit of the cosmic dark ages is dark and invisible to the naked eye, but it's not uninteresting. So you start from these small overdensities that we see in the cosmic microwave background, and under the action of gravity, those accumulate more material. And if I set this movie playing, you very rapidly go from something that looks very uniform to something that has these distinct filaments and voids, and sort of where the filaments intersect, you can see darker, denser clumps, which are halos. So each of those white spots is a speck of dark matter, if you like. As you do, eventually you start to form stars as gas gets dense enough to spark off nucleosynthesis. And then you have a question of what sort of stars will you form? So astronomers like to talk about 3 different populations of stars. Population 1 stars, like our Sun, are metal-rich. They contain elements heavier than hydrogen and helium that they were formed with. There were earlier generations of stars that produced these metals that got bound up into the population 1 stars. We also see population 2 stars, which are metal poorer, and potentially there could be an earlier generation of stars, known as population 3, that formed from just the primordial hydrogen and helium that was produced by the hot Big Bang. So before there are any heavier elements to build up. Now, we've never seen these population 3 stars, but you can make predictions for their properties. And at least in principle, they might be very different from the sort of stars that we see today. So in many of the models, these stars are very massive. They might be as much as 100 times the mass of the Sun. Very bright, maybe 20 times that of the Sun. And because of that, they could be very short-lived, maybe living only as little as 1 million years or so. So these are stars that live fast and die young in the same sort of movie parlance. And as these stars live and die, they'll throw out metals that enrich the next population and the next population after that. So just to give a bit of a sense of how these might form, I just wanted to play a movie from a group of simulators at Stanford. And in this, you'll see the sort of effect of the first stars forming and their light impacting their surroundings, heating it, and as they die, sending out a shockwave. And it just gives a bit of a feel for what's going on. So this is a simulation of gas and gravity. Here you see this white as a dense region where material is collapsing down on some central region, and at some point nucleosynthesis starts and you get a star. Its light is pushing away the gas, and at that point it exploded and sent out a supernova shockwave. And so that will have heated and thrown out metals with it. As time goes by, there'll be some other region, probably the next most dense region, And somewhere over here, you'll get a second star that will form. And so here, you see materials fallen on there. Again, light heating, a nice explosion, one of these nice shock waves. And after a little while, there'll be a third star that will form. And so making these sort of simulations is very much cutting edge to try and capture all of the physics and try to understand not just the small scales of where the stars are forming, but also the relationships between where they form. And possibly if you look at this, maybe you get a sense of these stars as being almost lonely. There's one star at a time in this simulation, and each one lives and dies before the next one has a chance to form. So, as said, I mean, in many of the models that we have, these early generation of population 3 stars were very massive and very short-lived. And so you wouldn't expect those to be around today. But it's not necessarily the case that all of these stars will have lived and died early on. If you had some low-mass population 3 stars, those have a much longer lifetime. And some of them could have a lifetime which is longer than the age of the universe, and so still be around. And so you might ask the question, can I go out and look for these population 3 stars today? And in fact, maybe you can. So cosmologists have this idea of hierarchical structure formation, where you form small galaxies early, and they merge over time to form larger galaxies like our Milky Way. And so bound up within our Milky Way may be elements of these earlier structures and earlier generations of stars. So if you go around in the Milky Way and you look for low mass, very low metallicity, very metal poor stars, maybe you could find some of these very old population 3 stars. And that's exactly what some of my colleagues, so Anna Frabel, for example, at MIT, try to do. And that every so often there's a bit of a buzz where they find the new, most metal poor star. And some of these stars, you can analyze the patterns of metals that they contain to be able to say that these stars formed as not the earliest generation of stars, but maybe the second generation of stars containing metals that came from just a single supernova explosion beforehand. So that's often known as galactic archaeology. It's less like archaeology and more like having a sort of great-great-great-great-grandmother that you can go and ask for stories about her childhood. But quite fun. So you have stars. Stars form galaxies. And there's a question of if the sort of description that I've given you of those first stars, of this bursty formation with each star heating and ionizing and affecting its surroundings, what do those first galaxies look like? It could be that early galaxies didn't have many stars in them. Stars were switching on and switching off very quickly. If the feedback, the effect of the heating and the ionization was more mild, then you might get more continuous star formation and get galaxies that looked more recognizable to the ones that we see today. There's a sort of an open question of whether these early stars were prima donnas or team players, if you like. And there's also a question of what sort of light did these early galaxies produce. So there was starlight, depending upon what sort of stars they contained. But as those stars live and die, they leave behind a remnant. Some of them will produce neutron stars, some of them will produce black holes. Those black holes can accrete matter and grow, and in that process of accreting matter, produce very energetic jets of light or X-rays that come out, and that light can heat and ionize the surroundings. And in many of the galaxies that we see today, the active AGN, active galactic nuclei, the amount of light coming from that central black hole outweighs that comes from all of the stars that are contained in the galaxy. So there are many different sort of sources of light in the early universe as you start to form galaxies and as they begin to evolve. And one of the effects that they have is to produce ionized bubbles. So if light that has an energy greater than 13.6 EV, electron volts, is produced, it can separate a hydrogen atom into the component proton and the electron. And so you can imagine this as sort of little bubbles of ionized gas around individual galaxies, that as more stars form, those bubbles get larger. Eventually those bubbles will begin to merge, and eventually percolate so that all of the universe is filled with ionized gas that's been ionized from the light from the stars. And that process is known as reionization. So just to sort of give you a sense of what that might look like, this is another movie that shows a three-dimensional box in which you'll see galaxies, and around galaxies you'll see these ionized bubbles seen as a sort of transparency in the simulation. So here you've got this three-dimensional cube that's rotating, and you can see galaxies, and you can see these bubbles that are slowly moving out. These bubbles are getting larger, and eventually they start to merge in quite a complicated topology of connecting channels and isolated regions. So, I don't know what this reminds you of. Maybe it reminds you of a sponge. It always reminds me of a Borg cube. Resistance is futile. You will be illuminated. That joke's a forte. And so, this is something that we believe happens in the early universe, this reionization. And it's yet to be detected. Eventually, all of these bubbles overlap, and that's what they're doing just at this moment. And you're left with just the light from the galaxies, which travels more easily through the ionized material. So this is a phase transition, and astronomers, scientists, we like to study phase transitions to see what we can learn from them. In many ways, reionization is the last major phase transition. The earlier one was the formation of the cosmic microwave background, where you went from ionized to neutral, and then with reionization you go from neutral to ionized. And because we haven't observed it, there are some very basic questions that we still like to answer. When did this happen? How long did it take? What were the sources that drove it? Which of these sorts of stars or AGN? How did this topology work? Were these little bubbles that around individual galaxies, or more collective phenomena around lots of galaxies? And it's always tempting when you give a talk like this to suggest that we have all of the answers. And just to sort of dissuade that, I wanted to make another movie sort of metaphor. I think most people would agree that Casablanca was a classic movie, and hopefully reionization will be a classic area of science. And so I've spoken, so we can compare these two things. So I've spoken a little bit about these different sorts of stars and galaxies, about black holes that are accreting and radiating. I didn't talk about dark stars, but there are models where rather than the nuclear fusion at the center of a star producing its energy, you can have dark matter at the center of a star, which is annihilating, and it's the annihilation of the dark matter that produces the energy from the star. It's quite an exotic model, but the numbers sort of work out. And so in some ways, this is the cast of the movie, and we can compare that to Casablanca, where there are taxi drivers, there's a policeman, there's this guy called Rick, Laszlo, Ilsa, a guy with camel, and we know that all of these things are likely to contribute to reionization, but we don't have a good sense of which is the leading lady, which are the bit players. Do these population 3 stars play a major role, or do they just come on for one scene in Act 3 and then are never seen again? And so this is the sort of question that we'd like to answer. How important were these different sources at different times? And in the same way, I can describe reionization to you with a simple plot. The universe was neutral, luminous sources formed, and then the universe became ionized. And that's a little like telling you that Casablanca is a movie in which a boy meets a girl, the boy falls for the girl, the boy loses the girl. Which is very accurate, but probably describes many, many movies that you've seen. And so what we're interested in is going beyond these plot highlights to really know the details of how these different sources come together and what the picture, what the movie looked like. And so in some ways what we'd really like to be able to do is to go out and observe this movie of the history of the universe. You live in LA for long enough, you can, what can I say? And so the question is, how might we observe this? yeah, how might you observe reionization in this period of the cosmic dawn? So I sung the praises of the Hubble Space Telescope at the beginning. And so the obvious thing to do is to try to build a bigger space telescope to see more galaxies, and from that learn about what's going on. And that's something which NASA and the European Space Agency are working on at the moment. There's a telescope, the James Webb Space Telescope, which has been proposed and has been hoped to launch for a long, long time, but now we're promised it will launch next year in 2018. And so this is it's not exactly a larger version of the Hubble Space Telescope. It's an infrared telescope that will unfold in a complicated and somewhat scary way to look at. And because it's an infrared telescope, it's geared to see more distant galaxies whose light will have been redshifted by the expansion of the universe. And so it will be fantastic, but there's a challenge that it will typically see only the brightest of these very distant galaxies. But the processes I've been discussing are driven by much fainter galaxies. And so just having a new big telescope is not going to be sufficient. So you want new techniques that will tell you not just about a few of the bright galaxies, but will tell you something about how the neutral hydrogen gas gets ionized. And that's really, that technique is really what I want to talk about. So it leads into new radio telescopes that are being built. So if you look at a hydrogen atom, you have a proton and an electron, and they both act like magnets. And you know that with magnets, it takes energy to move them from being sort of north to south to north to north. And it's exactly the same with the spins or magnetic moments of protons and electrons. And so if hydrogen flips from having both spins aligned to having the spins anti-aligned, there's a change in energy, which means that it will emit light. It emits light at a wavelength of 21 centimeters, which is a nice, sensible wavelength. You know, you can imagine what that looks like. And those wavelengths, 1.4 gigahertz, they'll travel through the universe and they'll come to us today. And so this is something that we can go out and try to observe. So the 21 centimeter line has been observed for quite some time. From shortly after World War II, radio astronomers went out and started to measure it in the Milky Way as a means of mapping out neutral hydrogen within our galaxy. And the way that works is that if you see hydrogen gas that's moving at a different speed from us, its light will be Doppler shifted, it will be shifted to a slightly different frequency. And so if you imagine that this is the sun, and the center of the galaxy is down here, and all of the stars and clouds of gas are rotating around. If I imagine a cloud of gas here, if I go further away from the galactic center, things tend to be rotating less quickly. And so, comparatively, it appears that the sun is catching up with this cloud of gas. And so that cloud of gas looks as if it's moving towards us. And so as light is blue shifted and shifted to a slightly higher frequency, and by more as you go further out. And so if you look at frequency and what you see, different clouds of gas will produce different peaks at different frequencies. And you can use that to try and work out how far away those clouds of gas are, and so map out the shape of the Milky Way. And this is an example of the sort of maps that people have produced. So the white here is the emission from hydrogen gas. The sun is somewhere up here. And you can see these sort of spiral patterns, which are the lanes of neutral hydrogen gas. There's this zone of avoidance on the other side of the galaxy where it's hard to map out this sort of distribution. So this is what people are able to do within our galaxy. And what we'd like to be able to do is to push this to greater distances, where the motion isn't coming from motion around the galaxy, it's coming from the expansion of the universe. And the idea is that different distances will produce different frequencies at this redshifted 21 centimeter light. And so by observing at different frequencies, you can piece together a three-dimensional map of the universe. And maybe the movie of reionization that I showed you earlier looks like something like Swiss cheese, where the cheese is the neutral hydrogen gas and the holes are the ionized bubbles around galaxies. And so we could hope to go out and make lots of observations and produce a three-dimensional map like this. So the question is, where do you need to go and look? So if you want to focus on this period of cosmic dawn and reionization, you're interested in a period from about 100 million to 1 billion years after the Big Bang. And that corresponds to frequencies that are about 200 megahertz to 50 megahertz. So if I tell you 100 megahertz, that's probably a frequency that you're familiar with. It probably corresponds to near a radio station that you listen to. So whenever you're listening to your favorite radio station, that's noise, which is getting in the way of radio astronomers measuring this cosmic signal. So please stop. So we need to build FM radio telescopes. So radio telescopes have a long history. This is a picture of Karl Jansky, and one of the first radio telescopes. So this is a New York Times article from 1933, where it's the detection of radio emission from the Milky Way. So Karl Jansky was hired by Bell Labs. There was this funny source of radio interference for wireless communication, and they wanted him to get to the bottom of it. He built this telescope. So this is wire frames, wooden frames, and then a few wires. So these aren't complicated bits of kit to build. It's fairly simple because the wavelengths of the light is so long. So once he identified that this interference was coming from the galaxy and it was impossible to get rid of it, they stopped caring and they moved him to a different project. And he didn't do any more radio astronomy. So one of the challenges that we have is that the 21 centimeter signal that we're looking for is very weak, and so you need a very sensitive radio telescope to see it. The obvious way of getting more sensitivity is to build big radio telescopes. So this is a picture of the Green Bank 300-foot telescope. It sounds like most of you have been up to Jodrell Bank recently. You've seen the Lovell telescope. So this is a telescope that was comparable in sort of size to that. And so building a big telescope is good, except when this happens. And so, sorry?
Starting to worry me now.
So one fateful morning in 1988, this is what radio astronomers saw. And as I understand it, just one small element in the supports gave way, and what you have here is huge amounts of metal, and under its weight, it just collapsed under its own weight. So big is good, but it's also hard to build and get right. I'm sure this won't happen to the Hubble telescope anymore. And so, in order to get big telescopes today, rather than trying to build big dishes, so the largest dish telescope is Arecibo, which I think is about 300 meters across, and so that's built into a natural bowl. And the Chinese are building a telescope called FAST, which is a similar sort of design, which is maybe twice as large. But that sort of natural geology is hard to find. And what people tend to do is to use a technique known as radio interferometry, which I can't describe and do it justice in one slide, so I apologize for that, but just to give a flavor of the idea. So the idea is that rather than building one big telescope, is to have many small telescopes and combine the signal from all of those to imitate a big telescope. So you can imagine that you have many dishes. Each dish samples the electric wave from the light, which it converts into a voltage. And then you can multiply together the voltages from different telescopes and look at the time dependence of that, correlate it together. And by combining all of these signals from many different pairs of dishes or antenna, you can synthesize a big telescope. What you're actually measuring is something like the Fourier transform of the telescope, which, as I say, I can't explain in. It's a talk in itself to describe interferometry, and I sometimes get confused myself with things. So, just to give you some examples of some of these telescopes. So this is a telescope known as the Giant Meter Radio Telescope in Pune in India. So it's one of the first of the low frequency interferometers. So this is, there are many dishes located in this sort of Y shape. Each of them has this large concrete base, and then if you look at these dishes, they look empty, and that's because you're looking at long wavelengths, and all you need is for your mesh to be smaller than the wavelength of the light essentially. There's an amazing movie where they filmed the construction of this, and this being India, it's done with ropes and pulleys and lots of people to haul these dishes into place and stack them. If you Google it, it's quite incredible. So this is 30 dishes, and it works at about the right kind of frequency range for these kind of cosmic dawn studies. But what people are doing now is to build new telescopes purpose-built for this kind of astronomy to target this 21 centimeter signal. And in some sense, these are 21st century telescopes, in the sense that they would have been very hard to build before the 21st century, because they're very dependent upon computing power. So this is an example of a telescope in the Netherlands called LOFAR, the Low Frequency Array. I don't know how well you can see this from the back, but these are white, basically polystyrene tubes with 4 wires coming out at right angles from the top, bungees to hold them in position, and basically chicken wire at the bottom to act as a ground screen. So the total cost of one of these antennae is about 70 euros. Very, very cheap. And it has to be, because the telescope itself is composed of tens of thousands of these elements. And so the unit cost needs to be small to have all of those. And so the way this works as a telescope is you take many of these antennae, you collect them into a single station, and then you have many stations, and you take the signals from those stations to a supercomputer, and all of the steering and the pointing of the telescope is done by introducing time delays between your electrical signals to digitally steer the telescope about. So there are no big moving parts or anything like that to go wrong. And this is just to zoom out on LOFAR. So there's a central core in sort of northeast of the Netherlands. As you know, the Netherlands is a very wet country, so this is raised up, and there's a sort of a nice natural, it's like a bird sanctuary these days, you know, herons and other nice things. And then the angular resolution of these telescopes is essentially the wavelength of the light that you're looking at divided by the longest spacing between stations in your telescope. So if you're talking about meter wavelength light, and you want to measure angles that are 1 part in 10 to the 3 of a degree of a radian, then you need sort of kilometer long baselines. And the longer the baselines you can have, the better the telescope will be at making nice images. So these, as I look at this, I see 4 dots in the UK, and I think there's only 1. So this is an old picture, but down at Chilbolton outside of Oxford. Sorry?
There's one in Ireland.
And there's one in Ireland as well. Ireland has been removed from this image beforehand. And there are in Sweden and other European countries. So these telescopes become very large. And LOFAR is currently in the process of looking for this 21 centimeter signal. There aren't any detections, otherwise I'd be showing you data, but we're starting to get optimistic that a detection will come soon. So rather than talking about that, I might talk about the future of these radio telescopes. So the next big radio telescope that's going to be built in this area is the Square Kilometer Array. And this is a picture of an artist's impression of what the Square Kilometer Array will look like in Australia. So this is a telescope that will be built partly in South Africa and partly in Australia. It's one of those things where, faced with the decision between 2 countries, they chose both. Which is less crazy than it sounds, because the 2 telescopes look at different frequencies. So Australia does the low frequency bit, and South Africa does more of a mid-frequency bit, which is useful for lots of cosmology. So this telescope is hopefully will switch on in 2024. The headquarters is, the international headquarters is in Jodrell Bank up in Manchester. And the first phase of this telescope is expected to cost about 650 million euros. It's an international project with partners from South Africa, Australia, the UK, Germany, not Germany, sorry, India, China, a lot of different countries. And one of the reasons that governments are very interested in it is it's very much a big data telescope. It requires a lot of computing power to process the voltages from the different antenna requires a lot of expertise in shipping large amounts of data around and developing all of the algorithms to do that. And so the countries hope to get a lot of industrial return on building this. So it's beyond me to fully convey the size and scope of the SKA. So I have a movie to do that for me. It's a slightly old movie, but let me plug it in. It has a fancy soundtrack. I don't know if that comes through. No? It's fine. I'll pull that out then. So this is, as I say, this is an old movie, so it has all of the telescope in one site. So it has these dishes, which are the mid-frequency part of the telescope. And I've talked mostly about the cosmic dawn side of things, but this telescope will do lots and lots of astronomy. So everything from trying to study the formation of planets, to the search for extraterrestrial intelligence, to mapping out the distribution of galaxies and doing cosmology. So in South Africa, there's going to be a lot of these dishes. And at the moment, there's a telescope there called Meerkat, which is similarly a dish-based telescope. So the design of the dishes has changed somewhat since this movie was made, but it sort of maybe gives you a sense of what it would look like. And there are sort of 3 different technologies that are being developed. So this is what the low-frequency bit will look like, except with those kind of Christmas tree-like antenna that I showed on the previous slide. But you have to imagine that there'll be hundreds of thousands of these scattered about the Australian outback, far away from people making radio signals that will get in the way. For the second phase of SKA, they're talking about a technology called dense aperture arrays, where you cram all of these dipoles together in order to make your telescope. So in South Africa, this is being built in the Karoo. Again, locating these far away from people is a good idea, although it leads to challenges in getting astronomers there and computers. And the general design is to have some central core, but then have spiral arms that come out from that core in order to increase the baselines and improve the angular resolution of the telescope and its general image-making properties. So the grand plan is that there'll be arms which are hundreds of kilometers long. In phase 1, it's much smaller than that, tens of kilometers. And so this is starting to talk about what a radio telescope would look like over the 21st century. These are very modular, and you can imagine building them out over time to get something which is really quite spectacular. So this is the low frequency bit. These Christmas trees were designed in Cambridge, and there's a lot of UK involvement in the design work and the science side of things. How am I doing for time? Not too bad. So I've painted an optimistic picture because I'm a theorist and I like to be optimistic. But this is actually a really hard measurement to make. And so if you want to measure this 21 centimeter signal from the cosmic dawn, you first have to remove radio emission from the galaxy, from radio bright galaxies, all of the sort of man-made RFI that gets produced. And in principle, these foregrounds can be maybe up to about 1,000 times larger than the signal that you're looking for. And so you have to exploit quite clever statistical tools in order to try and separate out signal from foregrounds. And that's the sort of challenge that people are just now starting to overcome. If you can succeed, the payoff is quite substantial. So whereas the cosmic microwave background was a photograph of the early universe, the 21 centimeter signal really is much more like a movie, because by looking at different frequencies, you can see different moments in the history of the universe. And so this is just a slightly technical figure from a paper I wrote a while ago. So this is showing the early universe evolving into the late universe with a two-dimensional slice through the 21 centimeter signal. So if you can see, there are sort of these kind of bubbles that get larger and then percolate up here. And different phases earlier on where there's different physics of heating and illuminating the hydrogen gas with other wavelengths of photons. And so if you can measure this, you start to pick out key moments in the history, sort of when the first galaxies form, when heating from X-rays and the formation of black holes forms, and this period of reionization. So there's a lot of the major moments in the cosmic history that you might hope to fathom out. And the kind of telescopes that I mentioned, so LOFAR, there's also the Murchison Wide Field Array in Australia. It's an experiment called PAPER, and now HERO in South Africa. Starting to probe the end of this region, and the Square Kilometer Array will go back even earlier in cosmic history. And there are plans to build radio telescopes on the far side of the moon, which is also good. You can go back to lower frequencies and escape the Earth's ionosphere. So we have a grand vision stretching out further than our funding will definitely allow. And, so, oops, that's a movie that insists on starting. So just to give you a sense of what these telescopes might actually observe, this is just a small simulation that I made of this 21 centimeter signal. And if I let it play, it evolves. You get, it's a bit fast, you get this blue, which is cold gas, red, which is hot gas. And after an early phase, more of heating, you start to get the growth of bubbles, and you see how they grow and merge, and eventually the neutral hydrogen is just all ionized, and your signal dies away. And so this is a movie from simulation, and the hope is that with these radio telescopes you could begin to make this kind of movie from the data and use it to learn about the evolution of galaxies at very early times. So what sort of things might we learn? Well, hopefully the answers to the questions I've sort of alluded to. Certainly simple things like when did the first galaxies begin to form, and when did they heat and ionize the universe. If you have these slices, then the sizes and the numbers of the bubbles are going to be linked to the brightness and the numbers of galaxies. And so you begin to be able to learn about what the stars are that make up the galaxies. The heating of the gas tells you about X-ray emission from things like black holes. And one of the things which is probably most fun is that at the end of the day you'll end up with a three-dimensional map of matter in the universe, which you can use to learn about cosmology and fundamental physics. That's probably harder, but it's certainly the long-term goal of filling in all of the here be dragons bits in a cosmic map. So yeah, that's sort of really the end of this story and the beginning of where the research comes in. So radio astronomy is going through this amazing evolution as computing power is enabling much larger radio telescopes to be built with many more stations operating at different frequencies and over wider ranges of frequencies. And as you get those new capabilities, you're able to attack new frontiers like the cosmic dawn and learning about the sort of first billion years of the universe. As I sort of alluded to, this is big computing, big data, all sorts of challenges, not only in terms of the algorithms, but for us as astronomers in trying to work out how you deal with these huge data sets and getting used to running high-performance computing on clusters rather than the sort of stuff that I can do on my laptop. And happily I have students that are more au fait with parallel computer programming. And these sort of observations of the 21 centimeter line, they may not answer all of these questions, but this is like artists where at some point you change from the sort of positive space to the negative space. The 21 centimeter signal, you paint the neutral hydrogen that surrounds the galaxies and use that as a way of inferring what the properties of those galaxies were. And with any luck, we'll be able to see how they evolved from very early on in the history and join up with what we see in the Hubble Space Telescope. So I think that's really what I wanted to say. I'm biased, and so I've talked about radio telescopes, but there are a lot of other exciting telescopes coming along that will shed light on this area. I mean, James Webb Space Telescope is something to look out for when it launches next year. But there's also a number of 30-meter class telescopes that are going to be built, mostly down in Chile, maybe in Hawaii. And the sort of image quality that they produce will be comparable to Hubble, but from the ground. And then there's other telescopes like ALMA that are able to search for molecules and things like carbon monoxide at the end of this sort of period of reionization. So it's really exciting times for this area of astronomy. And so I will finish that, and thank you for having me.
very much, Jonathan. Does anybody have any questions?
How long would the time lag be between the first atoms going neutral and the last atoms going neutral at the beginning?
So just repeat the question. It was what's the time lag between the first atoms
becoming neutral to the last atoms ceasing to be neutral? I think so. In the very early universe, everything we believe everything is ionized, and so the cosmic microwave background forms when the universe is about 400,000 years old, and it doesn't happen instantaneously. There's a sort of it's a fairly sharp process that lasts, about 10% of that time, I think. So maybe sort of 40,000 years to go from all ionized to all neutral, and then there's a long period of time before the first stars switch on, when the universe was maybe 10 to 20 billion years. And there's a lot of uncertainty to when this period of cosmic reionization completes. I mean, the furthest back we can see and tell that the universe is essentially all ionized is somewhere around about 900 billion years. And so somewhere probably between 600 million years and 900 million years is where everything will become ionized. And so you've got, on that kind of timeline, the age of the universe at the beginning is almost negligible, but it's sort of between about 400,000 years to about, let's say, 600 million years, plus or minus a few hundred million.
I'm just interested in the amount of how long it would take for it to originally become non-ionized, so all atomic material. The last time I asked this question to somebody else a long time ago, he said about 6 minutes, which sounds incredibly short. Now, 40,000 years sounds to me a little bit long.
6 minutes, okay. I guess I'm not quite sure what question he was answering. So, I mean, if you were
actually there, you wouldn't actually notice any change, because the radiation would be coming at you from here, and then it would be coming at you from 2 light minutes away, but it would be essentially the same. You wouldn't notice the difference.
Oh, so I mean, if you were sitting there, you would see a wave of light pass.
You wouldn't see anything, because the energy would be coming at you from there, and then it's coming at you from 2 light minutes away in all directions. You wouldn't see any change.
I'm not entirely sure we're talking about the same moment in cosmic history, but
Well, a conversation.
yeah, I think that, yeah.
Right at the back.
I understand the Casablanca analogy, but to me it's more like a ghost story. The fire you haven't mentioned is dark energy. I wonder what the impact of that is.
So dark energy is something that becomes important at much later times in the evolution of the universe. We tend to talk in terms of redshift, and I mean, dark energy becomes important below a redshift of about 1, which I always struggle, because I think in redshift I struggle to map to cosmic history, but I think that's when the universe was about half of its current age, so when it's about 7 billion years old. And so here we're talking about the first billion years. And so the dark energy doesn't really affect the evolution of the universe at that time. Since the evolution is dominated by the dark matter and other things. Yeah.
I'll continue the dark energy theme in terms of dark matter.
Go for it.
You mentioned being able to map the development of matter. Is it possible to determine, will it be possible to determine the distribution of dark matter and how that influences the relationship between galaxies?
So that's a good question. So there's a couple of approaches that you can use to try and use what you can see to learn about the dark matter which you can't. So one of them is that I showed this movie of a dark matter simulation where you get these filaments and sort of intersections of filaments, And in general, the galaxies will form at the intersections of these filaments. And so you can sort of use the galaxies as a signpost to say, I may not be able to see the dark matter, but I know there's probably more dark matter in this region than in other regions where I'm not seeing galaxies. And so you expect there to be some correlation between where the galaxies are and what the dark matter is doing. That's a very crude way of learning about the dark matter. I mean, the approach that people use sort of more locally to us is something called gravitational lensing. And so the idea is that just as with the Eddington experiment, where you see light being, the path of light being bent when it travels near to the sun, the path of light will be bent when it goes near clumps of dark matter. And if you have a screen of material, then you can try to work out how that light has been lensed by the dark matter between you and that screen. And if you do that, you can get some sort of very coarse map of what the dark matter is doing. So people do this looking at the shapes of galaxies, and you can try to do that with this 21 centimeter signal at higher redshifts as well. It's quite difficult to do.
Do you think that would produce a pattern which would be recognisable?
It's the sort of thing that it probably won't be very high resolution. I mean, it will sort of tell you there's more dark matter here, less dark matter here, more here, rather than, I don't know, anything very, very detailed. So it would be useful, but yeah, it's hard to know quite how far it will go.
I'm interested in the mega universe, and is the mega universe created by multiple big bangs, or is it just one big bang that we're talking about?
I'm not familiar with the term mega universe.
Well, beyond the
multiverse. What do I know about the multiverse, I guess, is part of the question. And what will this... So, I don't know. So everything that we're talking about here is within our observable universe. And so then people raise these questions about what happens if you go to the earliest moments in the history of the universe, and to do with the Big Bang. And
are we talking about one Big Bang or multiple Big Bangs?
It's really unclear. So there's a sense in which there's what we can see, and within what we can see, we will only see one of these universes. In principle, if you go back far enough in time, there could be this phase which is known as inflation, where you have this very rapid, accelerated expansion. And within that, little patches of a universe they stop inflating, and that looks like a Big Bang and produces a universe that looks like ours. And then beyond what we can ever hope to see, there might be other regions that have budded off at a different moment in time. And people like to draw these lovely diagrams of sort of almost a tree-like structure of different things budding off. I don't know. It's an interest. I like to talk about it to my cosmology students because it's an interesting idea. I'm not entirely convinced whether we'll ever be able to prove or disprove whether there's just one Big Bang or many.
Another one at the back.
Something you alluded to earlier in your talk, it's all puzzled by. Is there any light on the horizon with regards to European collaboration?
So my politics are very simple on this. I think this is all a huge mistake, and we will see what happens. So I plan on going to the House of Commons on Tuesday to lobby my MP, and there's an early day motion to flag up the importance of European collaboration. I mean, so one of the things which is important for say me, I have collaborators in the Netherlands, in Italy, in Sweden, and together we collaborate on this project. For funding our research, we hope to apply for what's known as an ERC synergy grant. And for these big projects, you need big pots of money that are larger than that which any one country can usually put together, an expertise that goes beyond what you typically have in one country. And so we need to be able to collaborate. I have lots of collaborators in the US, and the problem there is that we can collaborate, but we can't apply for the same pots of money. And so you scrabble around in your little area, you hope that you can find money for your bit, but everything is siloed. And the benefit of being part of the European Union and having these funding mechanisms is we break out of those silos and have essentially a larger scientific community that we move between smoothly. So I don't know. All we can do at the moment is write to our MPs with our perspective. I know scientists are doing that and trying to organise. There's a campaign called Science is Vital that would warmly welcome anyone's input.
It's hard to say in the long term what will happen to those that sort of funding. But, yeah. Any other questions? Oh, sorry. Yes.
Sorry, just to continue on that theme, if this gentleman would allow me. Just sort of what I was thinking about just now when asking that question was, without going too much into the politics of it, we've got sort of negotiations coming up with our European really all subjects such as we will discuss and so on, so this country can be in a position to secure as, should we say, beneficial position with respect to the European Union as we can. But one thing that did occur to me when I was thinking about this just now was that one of the benefits of withdrawing from the European Union, it may or may not persuade me, is that if we do withdraw from the European Union, then there will be a great deal of funding that surely would be available to us that would otherwise be spent in our contributions to the European Union. As far as our contributions to its budget is concerned.
So, I mean, there's a very specific and science-specific response to that. That is, when you look at European funding, the UK does disproportionately well in winning European grants. So that drawing a circle just around science funding, we are a net beneficiary from the European Union. Obviously, over the whole of funding for everything, we're a net contributor. And so there's a question of whether the government will be predisposed to give us a greater than our fair share, if you like, maybe, or what the government would choose to put that money to. So one of the nice things about these funding mechanisms is that they are, quite a lot of them are targeted at basic research, and you have the expertise across the whole of Europe for judging which ones should be funded. And again, all of these things are hard to reproduce on a small national scale. It's not impossible, but it will be a lot of hard work. But so I don't know. Maybe regardless, you have to fight, and you have to make MPs know that this is matters.
Point I was making earlier, maybe sort of all these negotiations come up that some kind of agreement can be made with all these various. I'll take that subject in mind, which require funding, areas of work require funding.
Fingers crossed.
Further on that, I'm saying that there is a risk that, certainly in my field, which is industrial research, we already know that the Treasury is guaranteeing up to to underwrite European projects you engage in until 2020. The problem with that, which is not what you get to see from the government press releases, is that in practice, because of the lead time to actually set these projects up, that in practice means that it is probably unsafe to make a bid any later than 2080 because of that. And I suspect much the same thing applies in your area as well.
Yeah. So yeah, there's obviously
A lot of uncertainty. Yeah.
Sort of moved on to question time rather than. But these things are important. We wouldn't be able to do this science if we didn't have the funding, and the politics is part of what we do. So it is important. But any last questions on the science aspect, or everybody happy? Oh, go on.
You mentioned the dark stars.
Mm-hmm.
How would you be able to detect them if you can't actually see them visually? Is there any way to detect them?
So you can see them visually. So the thing which is different about the dark stars is that, so you have a cloud of gas, and at the center of that cloud of gas you have dark matter which is annihilating, rather than in a normal star where you would have nucleosynthesis going on. So from the outside, a dark star looks like a ball of gas that is radiating energy. It looks sort of like a star. I'm not an expert on these. I think they look like more puffed up, so they look much larger, and so there are some, the details of the light they're putting off will tell you that it's a dark star rather than a normal star. But that's about as far as I can go on it, I'm afraid.
Okay, so I think that's about it. But thank you very much to Jonathan. Let's just thank him again.